Hello everyone, I am Dr. Padmasree Lam, Professor in Department of ECE at VNR VJEC. In previous video, we have covered analysis of voltage shunt feedback amplifier. In today's video, we will learn about analysis of current series feedback amplifier. Contents covered are derivation for transconductance with feedback, derivation for input resistance with feedback, derivation for output resistance with feedback of current series feedback amplifier. So this is the block diagram of current series feedback amplifier. In this current series feedback amplifier, basic amplifier is a transconductance amplifier. So conductance can be represented with G. Conductance is defined as ratio of current to voltage. Okay. So transconductance can be represented with GM. The GM is equals to, this numerator term is related to output terminals, denominator term is related to input terminals. So therefore transconductance GM is equals to I naught by VI. Okay. In current series feedback amplifier, type of sampler is used in a current sampler. So this is the connection for current sampler. In current sampler, input terminals of the feedback network is connected in series to output terminals of the basic amplifier. Type of mixer is used at the input terminals of the basic amplifier is series mixer. This is the connection for series mixer. In the case of series mixer, source must be voltage source. Okay. So now you can observe the input and output of feedback network. Input of feedback network is current signal, because input terminals of the feedback network is connected in series to output terminals of the transconductance amplifier. Therefore, in signal present at the input terminals of the feedback network is I naught. And output terminals of the feedback network is connected in series to input terminals of the transconductance amplifier. The signal present at the output terminals of the feedback network is VF. So once you identify input and output of feedback network, you can easily find out gain of the feedback network or feedback factor. Beta is equals to ratio of output of feedback network to that of input of feedback network. So output of feedback network is VF and input of feedback network is I naught. So therefore beta is equals to VF by I naught. Okay, and I naught is current flowing through the load resistance and VI is input voltage of the transconductance amplifier. In current series feedback circuit, fraction of the output current is sampled and converted into a voltage by the feedback network. This feedback voltage is applied in series to input signal. So feedback signal VF is proportional to I naught. Okay. So now we will see the derivation for transconductance with feedback. Transconductance without feedback, GM is equals to I naught by VI. So now we have to find out derivation for transconductance with feedback, that is GMF. GMF is equals to, what is the output current of the feedback amplifier? I naught. And the input voltage of the feedback amplifier is Vs. So therefore GMF is equals to I naught by Vs. Okay. So by applying KVL in the input loop, so you will get Vs is equals to Vi plus Vf. But Vf is beta I naught. Then this above expression becomes to Vi plus beta I naught. Okay, so from this expression, GM is equals to I naught by Vi, where GM is transconductance without feedback, that is I naught by Vi. From this expression of transconductance, what did you get? I naught is equals to GM into Vi. Substitute I naught is equals to GM into Vi. Then you can take Vi as common, Vi into 1 plus beta GM. Okay, so now you can substitute Vs in the expression of GMF. What is GMF? Ratio of I naught to Vs. So I naught by Vs is Vi into 1 plus beta GM. So instead of I naught by Vi, you can write down GM. Therefore GM by 1 plus beta GM. So therefore transconductance with feedback, GMF is GM by 1 plus beta GM. So what did you understand by seeing this expression? Transconductance with feedback is less than that of without feedback by the factor of 1 plus beta GM. So now we will determine the input resistance with feedback. So this is the equivalent circuit of transconductance amplifier. In equivalent circuit of transconductance amplifier, input terminals can be represented with Ri and output terminals can be represented with not an equivalent circuit. What is not an equivalent circuit? Current source in parallel with R0. Magnitude of the current source is GM into Vi, because transconductance GM is equals to I naught by Vi. So what is I naught? GM into Vi. Magnitude of this current source is GM into Vi in parallel with R0. R0 is output resistance without feedback. Okay, and output of feedback network is Vf. Beta is equals to Vf by I naught. Feedback factor beta is Vf by I naught. From this you will get Vf is feedback voltage, output of the feedback network. Vf is equals to beta I naught. So you can represent that feedback voltage in series with voltage source, as Vf. Magnitude of Vf is beta I naught. So the circuit represented in these dotted lines is equivalent circuit of transconductance amplifier. Now we will see the derivation for input resistance with feedback. But input resistance without feedback, Ri is equals to Vi by Ii. By applying KVL in the input loop, you will get Vs is equals to Vi plus Vf. But Vf is beta I naught. Therefore, the above expression becomes Vs is equals to Vi plus beta I naught. So this is equation 8. Substitute I naught is equals to GM into Vi in equation 8. Then Vs becomes to Vs is equals to Vi into 1 plus beta GM. But input resistance with feedback, RIF is equals to ratio of input voltage of the current series feedback amplifier to that of input current, Vs by Ii. Substitute Vs in the expression of RIF. So therefore RIF is equals to Vi into 1 plus beta GM by Ii. Hence RIF is Ri into 1 plus beta GM. So what did you understand by seeing this expression of RIF? Input resistance with feedback increases by the factor of 1 plus beta GM than without feedback. So what is the reason for that? In current series feedback amplifier, output terminals of the feedback network is connected in series to input terminals of the basic amplifier. That is why input resistance increases. So to determine the output resistance with feedback, that is R0F in terms of output resistance without feedback, that is R0. Okay. To find output resistance, set input source to 0. What is the input source of current series feedback amplifier? Vs. Vs is 0. What is the meaning for Vs is equals to 0? Voltage source can be replaced with short circuit. Short circuit, and disconnect the load resistance from the output circuit and apply the test voltage. V is the test voltage. V is the test voltage and I is the test current. Output resistance with feedback excluding load resistance, you can represent it with R0F. Output resistance with feedback including load resistance, you can represent it with R0F dash. Okay. So, but what is the feedback voltage? Feedback voltage Vf is equals to beta I naught. I naught is current flowing through the load resistance, but test current I is in the opposite direction of I naught. So what is the relation between I naught and I? I naught is equals to minus I. Then Vf is equals to minus beta into I. Feedback voltage Vf is equals to minus beta I. By setting the Vs to 0 from the input loop, you will get Vs is equals to Vi plus Vf. To find the output resistance of the current series feedback amplifier, set Vs to 0. Then this expression becomes to Vi plus Vf is equals to 0. Then what did you get? Vi is equals to minus Vf. But Vf is minus beta I. Then Vi is equals to beta into I. Output resistance with feedback R0F is ratio of test voltage to test current, that is V by I, by setting voltage source to 0. Okay. I is the test current. This current is dividing into these two parallel branches. So what is the expression for I? I is equals to V by R0 minus Gm into Vi, because direction of this current source is opposite to the division current of I. Then you will get minus. I is equals to V by R0 minus Gm into Vi, that is equation 9. Substitute Vi is equals to beta I in equation 9. Then I becomes to I is equals to V by R0 minus beta Gm into I. Okay. By rearranging the terms, this beta GMI will move to left hand side. By taking I as common, then I into 1 plus beta GM is equals to V by R0. From this expression, you will get output resistance with feedback R0F is equals to V by I, that is equals to R0 into 1 plus beta GM. So that is the final expression for output resistance with feedback. So what did you understand by seeing the expression of R0F? R0F is output resistance with feedback. R0 is output resistance without feedback. Beta is feedback factor. GM is transconductance without feedback. So R0F is greater than R0 by the factor of 1 plus beta GM. So what is the reason for that? In the case of current series feedback amplifier, current sampler is used at the output terminals of the basic amplifier. In the case of current sampler, input terminals of the feedback network is connected in series to output terminals of the basic amplifier. Therefore, output resistance with feedback increases in current series feedback amplifier. The circuit present between these two terminals, can be replaced with R0F. Then what is the expression for R naught F dash? R naught F dash is R naught F in parallel to RL. What is the name of R naught F dash? Output resistance with feedback including load resistance. R naught F is output resistance with feedback excluding load resistance. I think you clearly understood that how to derive the expression for output resistance with feedback including load resistance and excluding load resistance. Next, we will see the conclusions of current series feedback amplifier. In current series feedback amplifier, feedback circuit is connected in series with the input and output because type of the sampler is used in current series feedback amplifier is current amplifier. In current amplifier, input terminals of the feedback network is connected in series to output terminals of the basic amplifier. Type of mixer is used in this amplifier is a series mixer, and output terminals of the feedback network is connected in series to input terminals of the basic amplifier. So therefore, transconductance with feedback GM is equals to GM by 1 plus beta GM. So that means transconductance with feedback is less than that of without feedback by the factor of 1 plus beta GM. Input resistance with feedback is RIF, that is equals to RI into 1 plus beta GM. RIF input resistance with feedback increases than without feedback by the factor of 1 plus beta GM. Output resistance with feedback is R naught F, that is equals to R naught into 1 plus beta GM. So output resistance with feedback increases by the factor of 1 plus beta GM than without feedback. So these are the references used for the preparation of this video. In the next video, we will learn about current shunt feedback amplifier. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.